about 4.54 billion years ago, perhaps in just 3 million years, Earth formed. But how did Earth form? What were the steps in this process? Did Earth form gradually or suddenly? And what happened after Earth formed? This video will answer these questions. The standard model for the formation of the solar system, including Earth, is the solar nebula hypothesis. In this model, the solar system formed from a large, rotating cloud of interstellar dust and gas called the solar nebula. The solar nebula was composed of hydrogen and helium created shortly after the Big Bang, 13.8 billion years ago, and heavier elements ejected by supernova about 4.5 billion years ago. The nebula began a contraction that may have been triggered by the shock wave from a nearby supernova. A shock wave would have also made the nebula rotate. As the cloud began to accelerate, its angular momentum, gravity, and inertia flattened it into a protoplanetary disk perpendicular to its axis of rotation. Small perturbations due to collisions in the angular momentum of other light debris created the means by which kilometer-sized protoplanets began to form orbiting the nebula center. The center of the nebula, not having much angular momentum, collapsed rapidly. The compression heated it until nuclear fusion of hydrogen into helium began. After more contraction, a T-Tauri star ignited and evolved into the sun. Meanwhile, in the outer part of the nebula, gravity caused matter to condense around density perturbations and dust particles. The rest of the protoplanetary disk began separating into rings. In a process known as runaway accretion, successively larger fragments of dust and debris clumped together to form planets. In the late stages of accretion, the proto-Earth grew by accretion until its interior was hot enough to melt the heavy siderophile metals. Having higher densities than the silicates, these metals sank. This so-called ion catastrophe resulted in the separation of a primitive mantle and occurred only 10 million years after Earth began to form, producing the layered structure of Earth and setting up the formation of Earth's magnetic field. J.A. Jacobs was the first to suggest that Earth's inner core, a solid center distinct from the liquid outer core, is freezing and growing out of the liquid outer core due to the gradual cooling of Earth's interior. At this point, we should ask, what evidence do we have that this is how Earth formed? The solar nebula hypothesis is supported by several lines of evidence. First, meteorites represent the most pristine samples of early solar system material currently available for study. Many of them contain calcium, aluminum-rich inclusions that are the oldest materials in the solar system, dating back 4.567 billion years. Their isotopic composition matches that of the sun, and their mineral assemblages require temperatures greater than 1,000 degrees Celsius, but less than 0 degrees Celsius, which can only be explained if they formed in the hot inner region of a rotating protoplanetary disk. Secondly, the orbits of the planets are coplanar to within a few degrees, indicating that they formed in a thin disk. Also, nearly all the planets and known asteroids orbit the sun in the same direction, implying that the solar system as a whole rotates and that the material in the solar nebula was initially rotating. Furthermore, all the planets except Venus and Earth have synchronous rotations, meaning that each planet rotates on its axis once in roughly the same amount of time that it takes to orbit the sun. This strongly suggests that the planets were spun up by a large-scale event such as accretion from a disk. Finally, computer simulations show that it is easy to produce models of planetary systems that closely resemble our own, under the assumption that the material in the solar nebula was in a thin disk. These observations and arguments strongly support the solar nebula hypothesis. It's me! If you enjoyed this episode, please subscribe to my channel. Thanks for watching. See you next time!